auditorium. As a courtesy to all our guests, we ask that all cell phones and pagers be turned off at this time. Also, no recording or photography of any type is allowed. Thank you for joining us and enjoy tonight's event.
Good evening. My name is Tom Sofer. I'm the chairman of the Division of Physics, Math, and Astronomy here at Caltech. Before I introduce tonight's speaker, let me announce that our next lecture in the Watson Lecture Series will be on January 30th and will be given by Professor Tracy Dennison of the Division of Physics, of Humanities and Social. Love or money, marriage and economic development. Tonight, it's a great pleasure to introduce our speaker, Harvey Newman, who is a professor of physics. Harvey received his undergraduate and graduate degrees from that technical school in Cambridge, Mass., whose most illustrious graduates are Click and Clack of Car Talk fame. Harvey's been a member of faculty since he did big science. He works in high physics, and he began his career as a leader of the Mark J. Collaborative Line at the DESI Laboratory in 1979. Harvey's been under the Compact Solenoid, or MES collaborator, at the Large Hadron Collider, or LAC, since 1994, and worked on the U.S. version of the SSC for 6 years before that. So in total, he's worked on the experiment for 25 years, roughly half scientific career. The LHC and its two main experiments, CMS and ATLAS, have been described as the most expensive, most complex scientific project ever undertaken. All of this effort paid off handsomely last year with the announcement on the 4th of the start of the Higgs boson. Quote Science magazine, for all the hype, the discovery of the Higgs easily merits recognition as the breakthrough of the Harvey and his team, including his colleague Professor Maria Sarapoulou, have a central role in this great effort. In addition to his spectacular physics, Harvey has been a great mentor to Caltech students. Besides graduate students, he and Maria have mentored 90 undergraduate students. Clearly, he's had a great influence on education at Caltech. Been a great 150 years, having chaired the collaborative board for over 8, and he now serves as chairman of the U.S. LHC Users Organization. As leader of major national projects, Harvey has worked across the Atlantic more than 100 times. And I've heard but Harvey's a fellow of the American Physical Society honorary degree from universities in Romania and Brazil. Tonight he will share with us the excitement of discovery in the Large Hadron Collider. After his talk, he will take informal questions up here at the podium. Now I'll introduce our speaker, Harvey.
Thank you, Tom. It's an honor to be here with you 3 years after my last lecture to take us through the journey that we all shared, coming up to the discovery of a new particle called boson, which may be the Higgs boson of the universe. To show miles along that road, and most importantly, show you a view of what may lie beyond, because quest for new knowledge is a true purpose of our science and work. So in the course of the lecture, I'll take you through a view of the half-century research, what a theoretical work, the LHC experiment, process of discovery, what we on this model in C. Hughes, the lecture, the first part of LHC, some of them which will come in the course of the lecture. And this view of collisions of the very intense environment that we live in, an old comment. The particle physics, that field, asks the most fundamental question in the nature of matter. What are the most big constituents of matter and the forces, the interaction between them at the most basic level? What origin and composition of the universe are those constituents that we see today the same things as we saw in the early universe? It's these questions and these types of questions that have brought some of the best and brightest students around many at Caltech. And I'm here to mentor not only students, but many extremely graduates, many of whom are now senior members of our physics community. These are the readers of the discovery. These are the members of our group, and many students, graduate students, young staff, postdoctoral. And I'd like to highlight some of our most recent undergraduate work at CERN summer and participated in this exciting discovery. This is that milestone on July 2012, we got California time, when they went for experiment by MS, by Atlas, of this factors that contributed to this project, including the present director, that I announcing this discovery. This was the culmination of the 50-year process. The theory first formulated starting in the 60s, the LHC experiments conceptualized in the 1980s, the beginning of construction of 2001, and finally the operation in 2009. What did you last time years ago? I had a startup, although I'm very excited. And after a turn to machine started and experiments started magnificently, I already talked about the beginning of that last time. And here we are at this major milestone, not outside of man. And you can see the effect in many, both in Europe and also in other regions of the world at the time of that milestone. About the startup in 2008, you compare Google, show the collisions. And it was December 10, 2008, the accident night later. We started a magnificent year, and 2012 has actually been a bad year. So, the setup is a 50-year physics, which is a beautifully simple picture of matter in our universe. There are three families of quarks, which participate in strong interaction, which is the interaction that binds nuclei. And the first generation of these are what compose of neutrons in this normal matter. There are leptons, and the first generation of that includes the electron, so that here we can complete atoms, the first generation. The other generations have been discovered in muon, and so various generations of accelerators. Starting in the 1960s, for the strangeness in the second generation, then other quarks progressing actually in atom generation in more recent discoveries, culminating with the top of 1995. There's also a third generation of leptons, a heavy lepton called the tau particle 1975. And there are four cases of these forces describing three of the fundamental nature: the electromagnetic, the weak, and the strong interactions. Electromagnetism carried the front. The strong interaction carried by a subgluons, and the weak interaction are carried by two heavy particles. The U has no electric charge, and the W has electric. There are a number of shortcomings of this beautiful simple. It doesn't incorporate gravity. It doesn't describe what explains doesn't others such as Hadron optical masses, what nature were unified in the early universe, why there's a predominance of matter over antimatter in the universe we observe, and this and E and Gs tells us dark energy. So this is a beautiful, simple picture of these so many questions. The theoretical structures that we use start with field theory, the first of which was invented by our friend, following 12 years of struggle after long advice from his advisor at Princeton. This is all from 1947. A fantastic quantum theory of electromagnetism with extremely powerful predictive capability. Again, the unified theory, which all this came about, of electromagnetism, weak interaction that describes radioactivity. Together, these three gentlemen, after a long process, I will bypass Word and so on. The third fundamental theory, the extend model, was invented and by on faculty of Caltech, David Polliser, quantum dynamics. And elements is that quarks, which carry the short interaction at very high, have the same kind of interaction. Their interactions become weaker so that one can treat them in the same way as the other interactions. And of course, the key element, the one that describes how mass comes about, is the Higgs boson. This is just a little bit about that third theory, which I had some to do with revise for the chemical asymptotic freedom. The fact that versus a computer at high energies or short distances among the quarks. So I participated, as Tom mentioned, in the discovery of Hadron in 1979, and also you see here in another one of my previous experiments in the Large Electron Positron Collider, which occupied that same 20-kilometer tunnel that the Large Electron Collider now occupies graduate student at Caltech. Then we were searching for the Higgs boson. About the Higgs boson, the theoretical framework starts with an idea called spontaneous symmetry breaking. This is an idea that we see in history. The fundamental theory has some symmetry, but the states we see don't have that symmetry. Magnetism, where there's friction, magnetization in a certain direction, but there's no preferred direction in the theory. We see it in ice crystals, reading untamed to certain directions. We see it in the structure of snow. But what about a fundamental theory? A physicist named Nambu, who won the Nobel Prize in 2000, first called a spontaneous symmetry breaking. It could be the source of massive particles. His advisee, don't see these theories, but found instead that you produce, when you break the symmetry, produce massless particles. That two problems. One, question for mass. Two, are all massless particles which come in nature. Deland and in 1963 showed how, at this point, the symmetry difference from one phase from massless to mass in superconductors. And Peter Higgs, being guided by this and other earlier work, and others at the same time, showed how to transform away these massive particles that don't occur in nature and to keep the massive ones. And those happen. Building on the work of putting it all together. How to transform theory so massless particles are somehow eaten, like this, eaten, rise to the bosons, the fire massless, good in nature, and suddenly there appears the Higgs boson. The Higgs field is a vector field, and it fills the universe. And it is through the interaction with that field of particles that travel through the field that matter acquire, particularly the constituents of matter, the quark and the leptons. So, physicists, like as to the Higgs field, differing quietly throughout the universe, study same physicist, like a particle, is into the room, and it turns when they cluster about him. And about him, he finds each one will move around. And so that's just like the process of acquiring mass. In other words, just like a particle as it moves through the Higgs field. Okay, so now let's turn to particle physics experiments. What do we need? Accelerators. Accelerators to accelerate particles. The LHC accelerates protons to very high energy and to bring them to collision. Detectors such as CMS and our competitors, scientific instruments, consolidation that record particles and measure the process there and direction as they function, computing to take a worldwide ensemble of computer facilities and networks to store and enable us to analyze the vast amount of data, which actually amounts to millions of data per year produced by the detectors. Only a worldwide collaboration of scientists, engineers, technicians, can design, develop, build, and operate such a complex accelerators. Accelerators, of course, to provide sufficient energy so that we can create new particles on an energy scale and equivalently hasn't been achieved. Also to probe down to physics, to examine the force of nature on small details which haven't been accessible. So by going to Hadron, we effectively give ourselves resolving what we didn't have before. And the energy scales you reach in the cosmos in terms of equivalent temperature, and therefore there's a connection with what happens. And so accelerators like the LHC, we create particles that were rarely in nature after the universe created. What we see here on the left is actually a sequence of as you go up in energy, you can probe from atomic scale to the nucleon scale, and then to the constituents of the nucleons. And for these accelerators, CERN at Fermilab Stanford, provided foundation for which we're talking about tonight. They established this unified electroweak theory and the standard model of the strong interaction. The distance of the W and particle measured is very likely. These measure part in 1,000 and ultra new particles. One graph is clear data from the pre-accelerator electron particle, which first studied the Z particle. This is a logarithmic scale. So you see an enhancement by orders of magnitude studying the particle. The higher these, the W particle, the Z particle, and all the working for the Higgs. And down here at the bottom of what could have been a few events had they been there from the Higgs. And in fact, there was such an indication, which after a struggle and movement to be a statistical fluctuation. Enter the element of the topography of Switzerland and France, accelerator border. Here is a very important discord. Actually accelerated for 50 to 150 meters. Two major experiments are in that list, and I'll talk mainly about CMS. And in fact, really, the accelerator accelerate protons starting from a hydrogen bomb and through early generations of accelerators, finally the LHC, to 4 TeV per beam this year and 8 TeV in the center. That's the right machine. We've been looking at the standard model. By the time you reach the tera-elect scale, the energy scale equivalent to roughly 1,000 times the mass of a proton. The electroweak theory would essentially become strong and fall apart. It doesn't exist. Could be a photon, could be something else, particularly what the mass of the Higgs will be, could be as much as close to 1 keV itself. So suddenly a proton energy that constitutes the protons, which are, and actually the gluons, which hold it together, are those things which most collide that we study. You can see two sequences of Hadron colliders, that's proton-proton and antiproton colliders, and electron colliders, which are symmetry. These have a cleaner state. The electrons and positrons annihilate, or no fragments left over, all leading to new things. The energy of electrons are light, and it takes a lot of electrical to make up for that radiation. Lights can go there. The LHC are their proton machines. The first go well into the TeV scale. In searching for new things, to examine lots of possible different scales at once, and we'd like the protons contain quarks and gluons of many momenta, and therefore when we collide, creating these different state energy all at once. So a proton collider, the highest energy and the highest luminosity, which you can think of as is a machine. This is what indicates the difference between LHC and parts mass energy. This is on a log scale, many orders of magnitude, cutting off at about 1 tera electron volt, and the LHC going well beyond. And in particular, gluon collisions, which creates. So the LHC is a discovery machine into the T-scale, parallel scale. And there are many reasons to do physics. We found a particle that looks like the Higgs, but we don't know why not. And we know tandem for all the successes are in T. So the real search for all the possible things of nature, and after all, science is about new things. We do not know ultimately what we'll find. This is not the LHC. I've said some of this. There are actually two rings where bunches of protons circulate in 50 nanoseconds. They're very intense. There are order 100 billion protons in each bunch. And you can compare these two columns. This is an early cartoon of design values, and this is what has actually been achieved this year. You'll notice the energy is like the accident we put after we have this repairs going on starting this spring. We hope to go out to the pushy, but we already reached with half of the proton bunches line density. And in many ways, this is a really super instrument. The ability to accept protons, focusing power, the way of being, thinking as an analog of an optical system, you can focus a very small spread in position momentum space, are actually better than the design. And so this combines high energy and density. And it's that combination that allows us to store processes. Also, in this zone, discovery of Higgs particle, as you'll see, we're dealing sometimes with one collision in 100 trillion to find the key signals. This progress is called integrated luminosity. Here's our inverse. What does it mean? And sometimes means created of 7 trillion collisions. And so what the LHC has done up to the time of the discovery in Mai, we had receptor bars in 2001 and about 6 in 2012 at the time of the announcement. And after the LHC, and has since delivered quite a bit more luminosity. Overall, compared to the 70, we ran data, in 2011 data, that we had at that time. And all the progress that we put on. So after the advent and recovery, which I already talked about, we had a startup with some luminosity to see anything on this cell. That's a blow back of 100. And then we have this, which is the 7 TV data, now the 8 TV data. So phenomenal progress. Overall, in 2012, in terms, we produced 2 trillion proton times 10^15 in scientific notation proton collisions on the path of others that are next all complex ensemble instrumentation ever devised by mankind. Around the collision, you put specialized, each of which is designed to detect and measure a certain type of protons, electrons, which are the product of quarks. Quarks not actually appear in probodynamics. And as quarks fly apart, they pull other particles vacuum, and you see jet signals. Neutrinos escape and are seen indirectly as missing energy. When you add up everything, you have contents of total momentum of 0, and energy, and it's on neutrinos, or other weakly interacting particle, which is sector. So here's CMS, perspective view, sector cut out, so we can see how it works. It works, we'll see a bit more. So here's how different parts are used. Gluons travel through, inside the screen meters, muons go through, and they're also measured outside. The electron in the tracker, and most of the energy goes to crystals, 76,000 crystals, all Hadron track. And then most traditional hadron calorimeter, a charged hadron has attracted again with them, and a photon, no electric, no charge, it's any distance. This is a timeline of the CM radical design, highly modular, with a major component. Here you see my garage under construction. The major component first assembled on the surface and tested and then lowered down. You see some major elements. This is the heaviest element, 1,000 tons, was launched February 2007. It took 11 hours to go 150 meters or 500 feet to the ground. This is the superconducting solenoidal coil that generates a magnetic field of 40 kilograms. Compact muon solenoid, compact that doesn't be small. 12.5 tons contained in a volume. The stored energy in the magnet in gigajoules. What does that mean? This is the amount of energy to raise to the top of Mount Everest. It's also the kinetic energy of the largest man-made moving like this aircraft carrier moving at 20 miles an hour, 100,000 tons. That magnetic is drives the start particle. So here CMS exceptional subsystems like a silicon trinity prism in a normal system. Heavy crystal 90 tons, which provide precise measurements of electrons. Beautifully, it operates, it has operated the 15 that we collected about much of the amount of data delivered by the LFT. Usually the number of channels working every one of the is close to 10. Some of the things that Caltech has done, which I don't. The heavy crystal insulators, which I used to measure the crystal laboratory, which was established first for studies for the SSC in 1983, has studied crystals in a range of experiments. As you rest, you can see that the crystals are smaller because they get more dense. High energy measurements, we need to contain more energy in a short space, and we also have developed synthetic tungsten, whose density is greater than that of iron. And light created in the can propagate to the detectors and be converted to electrical signals, and we can read out the result precisely where the amount of light and therefore the amplitude of the signal, the electrons and photons. You also see on the right, I'll talk a little bit towards the end about generation high luminosity, fast and bright and very the next of the LHC perhaps a decade from now. The light computing model, which I developed in 1999. You see a worldwide ensemble of computing facilities represented here that flows from the constructed into physics quantity first put at the CERN laboratory during 11. We also went into the first facilities that are used at universities and the smaller labs, of which are now 160. The nature of this ensemble as a system depends upon networks. So we react and now have the state of the art in terms of understanding and operating towards the highest point to relate and home transatlantic work into the field. This is one of them. It's a global, intelligent, autonomous system that monitors computer and many of the major links on research and education. Since the experiment started, the physics output has been a marked thing from the earliest. In 2010, with a small amount of data, which I showed you, we essentially went through the process of critical discoveries, the old discoveries, not discoveries, but discovering what was already known. And so this is a beautiful picture where on the top we show the original discoveries, apart from the same head called atoms, which were in a Mohn's eightfold way. The bound states of quarks, charm quark and anti-quark, bottom quark and anti-quark, the Z particles and the top quark. This is a span, as you can see here, 50 years. And investigating this, first cosmic rays on the surface, 2006. But with LHC, from summer 2009 until 2000, all these discoveries recreated. So we had, of course, and we're checking in a new thing that wasn't predicted by the standard model, and the answer was no. So Higgs, first 2000, only Higgs. There was a process of search for decades, and both direct and indirect measurements, precise electrical data at left, which I showed you, and we down the range. Soon, by the end of last year, we only had a narrow 13 GeV gap left. Very energy rich. In December 2000, mass of 3D, up near the limit where the things. How are particles produced? Okay, look at. Well, the leading way in which it could be produced is two constituents of the protons, which are getting together and fused. Now, the Higgs couples, it cannot couple to gluons directly, because then here channels can be other forms of matter. For example, quark in a loop particle leads to the production of the Higgs. That's the most copiated. But of course, it's hard to pick these events, and there are channels which also, a photon, a proton, one each, can come together. They can each radiate a W photon, and those together. I don't even cross everybody with less, but you get these additional support over more signature, and therefore it's useful to have a single photon wheel. The master of back events, this is an ology, a signature, we picked out more distinctly. There are other modes. We used the F was called associated particle in addition with a D or a Z particle. What do we look at? Well, once the Higgs, if it's produced, it's an evanescent particle. It has a very, and we can go to a pair of Z bosons or two photons. That'll be very important. Or a pair of W's, or leptons with that, and a bottom quark and a bottom quark. For the Higgs couples message that the most copious modes, most frequent, the ones of the heavy particles. But in terms of distinctly, we choose very particular. I wrote a particle going this loop to two photons. It's only 0.2%, a very small fraction of all the case, but very useful because it's so distinct. And another one is the two Z particles. Each goes to a pair of electron and positive and an anti-muon, two pairs in combination. 1%. And we use those two, and you'll go from it. This is a chart on the log scale of all the possible decay particles. The mass range of focusing, also liberal after all, but still in the need to take out and contribute. So now, showing how they all the bumper to the force carriers, the electrons, almost the ZZ, but even a subchannel of that. Only 8% for each Z goes to a pair of these leptons. And that's why we get all production rate, but very important. And also the pair of pulses. Eventually, we're going to bring all this together. And that's contributed in a very clear way, as you'll see, to the discovery. So this is the first, a very beautiful event. You see two ions coming out, that's these green bars, that's energy in the crystal. This is normalized to emphasize those events which most clearly identified, measured, point at which they emerge. Also reconstructed correctly to get the metaphysical by adding to a mass. And a key point is a high resolution of 1% in the central part of this subsector. This is a very important mode in the discovery. You Yong, who recently did his thesis and defended his thesis on November 7th. That's the interesting challenges. In order to use of that very distinctive, here at Caltech, we developed a system changes in all styles and crystals so that as their response varies with radiation in the LA response, one check every 3 minutes. The transparency changes in all. Then one can combine this another calibration method invented at Caltech and check the ability to rectifying a well-done process as E going to a plus or minus pair. We can check the proceeding in all the crystals containing the high resolution. Laser systems are developed and commissioned here, able to 1%, adjusting the 1%, and in some cases better resolution. Other key technique, using physics. With so many crystals, rate process, first mode of running, most neat thing is called the pi-zero. It only has mass in 35 MeV, a seventh of a GeV. We developed the technique to use this precisely. There was a special hybrid data speed of taking 7 cells and that allowed us to and this contributed to the discovery modes because we're getting high resolution for photons, and with the crystals, it contributes very high for electrons and positrons. As you can see here, this is actually also the first physics occurrence. We first had collisions of the LSD injection at 90 at the end of 2000, and also started operation. 70 here, the Times actually visited Pasadena, we're going to CERN. This is a celebration of this collision, and the first output, the resonance of the pi-zero, which started us on the path to and of the Higgs. An increasing power of the LED. Big challenge high. Every time inches of protons 50 nanoseconds, and saying when we reach it will be every 25 nanoseconds. Every 50 nanoseconds means 20 minutes. Every crossing, there are sections and up to 50. And here's a spectacular event. Many particles come out on a small scale along the beam, seeing many vertical interactions, particles coming into the detector. and yet hydrogen maintained. From the crushing from all this energy and the analysis that comes from the extra interaction. Next is a special passive event. There are two photons and jets. The rarer amount which I mentioned, where the two W bosons or the Z come together to form the Higgs, leaving over, and they'll take a quark and other quark which form jets of particles. Rarer, more distinct. By July, the June public, we clearly have data to see something. So now we use machine learning to optimize the signal bound discrimination. We also use mathematical techniques called likelihood fits. But to visualize, this is very important to see what's going on. See this mass distribution for photon pair. You see a sprout can produce real photon pairs, photons that you can fuse particles from jets. The enhancement, to start to see the enhancement. This is weighted in such a way, sort of like not just an illustration. This is the unweighted. Many people of these in my group have contributed. That's all in the discovery. I shall you being like Wong, who just graduated in this channel. You'll see actually work on another new physics channel you'll see in a moment, but for machine learning technology, things abound. And the other students now, Alex here, had a new event that will really improve this analysis. Many students are named here, and also many graduates, some of which gone on circulating some of the graduates are intrinsically. One of these, filtration, optimized identification on an accurate, precise energy scale, innovative analysis, and persistent. Well, the first thing you do when you're looking for such a thing is a thing you try to data. This is the level for setting bits, which corresponds to the standard backgrounds with no signal. We actually went below that with our sensitivity down here over this whole mass range. And this is what we observed. And there was an excess that we weren't able to set a limit as we expected. There's an excess of 125 GeV, both in 2011 and 2012 data. How do we know if it's significant or not? What are the odds? Now, what we're seeing is an upward clicking of just background. The normal process it out to Higgs. It's a few probabilities, and I'll try to describe them. First range. This is what we saw. Probability of background only, and when suddenly we saw this dips. Down here, the A are shown together. Probabilities are down here. They're very small values. What do they mean? What it says is a bit above 100,000 only. And so we convert models. It's the number of standard deviations away from the normal distribution. If you're standard 1 sigma, that happens in one direction, 1 in 6 times the often. By the time you have 3 standard deviations at 1 in 40. Like mentioned, the scientists have come to call our discovery. 5 standard deviations, 1 in 3.5 million is combination, also known in common language as a discovery. In this one check, the excess had a significant sigma, so strong evidence. Not yet. The next channel to followed. It's so distinctive. Become after relative. Here are 2 beautiful ends. One in which one Z goes to an apoptose, Z goes to N. And you can see the 2 muons and the electron and proton in this event. So electron and proton, and another beautiful involving 2 electron proton pairs. So from a common vertex, common origination point, you can measure the mass of 1-2%. What you see is a neural mass move backward. So some of the data will be 2 billion proton vision as well. This is both the data, and from 360 we see this enhancement. There are 13 events in that enhancement. We observe overall in that range 17 events, the exact 6.5. Signal to background. The signal events are 1 in 100 trillion. Probably we got the mass right. Both muons and electrons, but here's a beautiful result. There's a higher order process where a Z can go to 4 leptons. You have a decay lepton pair, one radiates a photon. It's called a virtual photon, and that creates an electron pair. And we can measure the Z mass with vertical side. It's a known mass. It was measured at left to 2 parts in 10 to 2 parts to 1,000, and we can see it in the right rate. So the normal spheres have right and all rated, and see that the right. So we can use this result. Is it the standard model? After all, it's the only variable of decision. In this channel too, the excellent background, 4.5 sigma. The point is 0.8 with the standard model, which in the way this is known to be 1, so it's compatible. We determine the two channels with precise mass determinations. We get very nice mass of particle. And now we feature best in terms of the here. Sigma strain is not much the standard model strain, and the dark colors are bit regions, and then one standard deviations around that best point. As I said, I give you several of the details. There is a grand comment on other channels, which, in the interest of time, I'm skipping. These high-resolution channels are the most important for sigma and most sigmas. There are also see indications due to the ornamental networks and the two caltons. And all of them fall short individually sigma criteria. Together, there's a sigma and sigma. The sigma combined is even plus minus 20% away from the model, compatible with the standard model. But the odds of background fluctuation only are 1 trillion to 1. How compatible is our signal? For rates, different channels. It takes the standard model these rates. Different values and their statistical errors. The green band is what happens when we fit everything jointly. You can see that the green band is not R1. There is some indication not every lined up exactly, perfectly, but within the curve, this is compatible with this mobile. So what we see is compatible with the expectation, but some channels require more data. And in fact, the most important thing would be, if we get more precise values and see a deviation, then we're seeing the breakdown of the standard model, which is the true purpose of our exploration, to find new physics processes beyond what we already know. We're also using these risks for different channels, measuring of the Higgs, compare how interact strongly with the different types of particles. Both the quarks and leptons, called fermions, make up the basic constituent matter, and the particles called bosons, the photon and nu, that are the forces in nature. And you also the errors here, but more or less line up with the standard model prediction of 1 normalized. Where do we go here? There are two very nice talks by two members of our group. One named Boucher, who spoke to the PMA Division Chair Council today and gave a very beautiful talk. Also, some work together. Boucher is a Miller Fellow. Emmanuel Moko is one fellow. And is a very talented graduate student in the group. The thing is measuring quantum properties of boson. The properties is channeled with two Z bosons going on, how the bosons are created, how the particles decay, quantum addition. Part of the issue is very computationally intensive. Along with the experimental investigation, one stage is done about how the data agrees and extends, and what is the property of this particle. What is its symmetry when if you change its charge? That is a particular symmetry of the particle to an antiparticle. What about the properties on the mirror symmetry called parity? Those are computationally intensive quantitative studies leading to new quantitative knowledge. I'm not finished talking about Higgs. Before I go on, I need the audio.
Meet the Higgs boson.
Sorry.
There's been a piece missing, a particle that would give other particles mass, unless it could be found in metaphysics and convolute that. In the 1960s, Higgs and from the University had first developed the theory of a particle or some unity of energy mass. It takes very tiny particles. The Large Hadron Collider, also between Switzerland and France, is a mega machine by any definition. It cost $1 billion. Protons were accelerated around the racetrack at speeds coming very, very close to the speed light, at which point they would collide and produce a smaller evanescent particles, and if one of them was the elusive Higgs boson. Number on the earlier runs of the parts. The The discovery of Higgs boson was hailed as a monumental achievement for a lot of reasons. First of all, it served and confirmed the standard model on which half a century of physics has been built. More important, it's on case deeper mystics.
So much for what made Higgs boson. It leaves us with so many questions. Even the present article, what's the big dark matter? Is physics in the early was unified into one big action? Why is gravity so weak compared to the other interactions? When things oscillate from one time travel? Why is the universe filled with matter and so little antimatter? Where does matter and particle come from? What dark energy? We know so much, and yet we know a list of questions. One is fired by what the hell can I afraid of symmetry? Speaking of the universe. Okay, what about the descent? As we know, normal matter is only about 4 or 4.5 all the universe. We don't have this. And what's its relationship to particle physics? We know, in amazing observations of Zwicky, that the atom is a mass and not the clusters. It doesn't have the dark matter to hold it together. If we look out on the large scale, the images of it distorted by some matter between Earth and where we are, and very strange effects. Visual, multiple images, an unfold map of what you see. One can unfold what you see, the actual dark will have no particle description. That's not accelerating views of the universe, but also depending upon the amount of energy, it dominates the entire structure of the universe, the radiance of matter. And okay, so our matter, there's time for matter. We know these metals as compared to normal matter. Could it be? More symmetry. For every particle we know, every particle, there's a partner. For quarks, it's quarks. For there are gluons. For these gluons, and so on. Why important? Such a compelling picture. Because in Rome, we try to go back to the universe, the Higgs mass essentially this provides us with the partners a way to moderate that explosion of the theory, have a stable mass. Supersymmetry tuning, it was found starting in 1982. And for most forms of string theory, the infections, this relies upon supersymmetry. Frankly, if such a model of physics, tandem model exists, there are these H-shaped normals, and eventually some. At the end chain, those supersymmetric particles interact very, very weakly with matter and would escape from the detector, leading to signatures, such as shown here, multiple energy from the energy escape detector. So how to find symmetry, or in general, how to search for dark matter? This is also an area where my colleague, Professor Sparopoulos, has a great expertise as in many of the. So Professor Sparopoulos and Chris Rogan have invented the razor technique. What this picture is a simple example. They take to leading to jet and also these weak particles which escape. And how to find out the mass of this hidden mass scale that results in these nucleus. By this new technique called the razor, one can use variables that measure the mass scale, also are sensitive to the missing signature of these events. And you go to a special frame, it's the final particle of the frequency mode in mass scale, a heat. And remember, I've done this in a powerful way. It's interesting many formal processes from standard model. This has turned out to be the most sensitive to search for supersymmetry. And in the parameter space of the possible various supersymmetric theories, here's an example where the analysis has ruled out a large region, but of course still left a large region still open. And as we progress at the LHC in luminosity and energy, in the longer term, we'll be able to explore much and find out if supersymmetry is source matter, and if supersymmetry is that more fundamental lies beyond the standard model. But in these, we've already reached beyond the 1 scale, hence the energy of the proton of that order for both. Another notion is for extra dimension. This is related to the question. Why is that? One of the ideas postulated is that we, in our standard model particles, live on a sort of memory space which has evidence, and only gravity essentially propagated the fiction. Why don't we send an energy of an acrobat, and here's the acrobat, Nick Walenda, and also an ant there somewhere crossing the Niagara. Well, it's very clear, as you can see here, it only move in one dimension, forward or backward. If we zoom in further, we see the ant, and he can move along and also around. And so that's the idea. When you look at things on a small enough scale, equivalently, you can look. So here's a picture, live and brain, here in a larger space. The Planck brain, gravity is mostly out of research. For new resonances, new particles that could swap through resonances in this space between two channels, plus or minus at very high energies now, and from 12 to the of 2,000 as 30% particles. Of course, since you don't see it in the newspaper, you have a Higgs boson at 125, so remarkable in other ways. Thinking about the century, such a mass is pretty heavy, and it's hard to fit in the simplest forms of supersymmetry. So what? No, he tends to subtle, perhaps a little smarter than we. So supersymmetry may not be so simple. And seeing this mass has actually spawned in this summer, exploring exotic things, not only model the forms of supersymmetry. Another exotic thing is us in a very strange scenario. The Higgs field, which fills all of the universe, defines our vacuum. But the Higgs is not heavy enough to maintain that vacuum for a time. So maybe the vacuum that we live in can suddenly disappear. They're in a tunnel to an and here region in terms of the Higgs, the mass calculated rather precisely in the last few months. This is the stable region, possibly here we are in the middle. But that vacuum may be stable, but for two months it lives for a long time. Because we're here, and we came from the universe when the energy was extremely high. We believe it's probably a sign of some new physics that lies in the back. And we're in the middle, and this is the learned just from that one fact, the mass of the Higgs particle. Okay, so I concluded a narrow in the midst of this enormous enterprise, CMS experiment, the late program. What role? Tom said we have multiple leading roles. Physics, which detectors triggers events, with data is recorded and aspects. Our focus is also broad front, not only the Higgs, but supersede alternative, other exotic form of physics, and this is in Maria, explore landscape, it's new physics, whether what you see, something exotic. To have it role, have more keys in a number of areas, as you saw, develop technology, innovative and new statistical techniques, in-depth understanding of the detectors, the computing, and the other. Systems are really the source of all. We've had some fantastic students. In 2011, there are 7 CM awards for working here, 6 enterprise solutions. In 2011, for work on the electromagnetic calorimeter, the crystal to calibrate precisely on the churn, and also on the Hadron calorimeter, and to make its performance much higher. 3 still work group at Caltech. 100 institutions. Actually, think about the statistics. Is that random? That's 5 minutes. As in these facts, undergrads are fantastic, and I think a unique resource. That's the privilege of mentoring 90 such undergraduates throughout my career, and since the arrival of Professor Sparopoulou, this has only increased. That's great. This is our 10 surf of Valère and Mac. We're different in full attempt, actually, we found. This is not the CMS detected autograph, so we were having a party, and they made autographs and surf it. Just think what it was like for these summer students who arrive at CERN during this, this project that had been built for many years and working to have a discovery would be greater. Okay, so we've had very many visitors. Here's June 9th, 2000. There's one visitor, Bill Gates. But the more arrived a few days later with the group, and this is there at the time. And we also had a nice visit recently from Ed Stone. Visited with our group. You see Ed there with and some of the students and fellows in our group. And here you see Ed Minutes, where our lead of the LAB team is explaining how the magnets are constructed, how they were, and he against the control, giving permission to be. So that's CERN, trust people from Caltech. Okay, so this picture, if I show that lecture, CMS, this new modular detector about 2009, just before physics. Right after this, another bit from Jean, some of you in the English. About future. This is the last one of this so-called luminosity. Down here is the star, and I had to add these apps to the previous to show that we actually did better in the early years than was early. But we're just 29 inverse femtobarns, 2 quadrillion collisions. In the coming years, we're going to have a shutdown to upgrade the accelerator so it's energy. Also, the noises will potentially do that. That's very promising. We'll take in luminosity to 5 femtobarns, about more than 15 times what we have now. Then there'll be an injector. Along the way, during these long tracks, will also be upgraded, a new tracker, and eventually in later years, also new calorimeters. So here, for 2022, we enter another phase called high luminosity LED. And to reach 3,000 inverse femtobarns, so 100 times the data we've had now to reach, but even that, because it'll be at high energy. And then beyond that, start 25, now we're really talking about next generation, a high energy LHC using the new high-temp superconductors used in superconductors to make magnets of 200 volts hours, provide energy 33 TeV compared to the design energy of 14. So we will continue to extend our reach. And at some of this very program, we will have more discoveries, and our thoughts about physics will change. In closing, there is active research and development going on. Our laboratory is working with this new crystal called LYSO, lutetium trioxosilicate, a fast bright scintillator, very radiation hard, and also studying hardness due to optical fibers in the zinc. And also Professor Baropoulos is on solid state photoamplifiers for precision imaging, come from the interaction in this very environment from all the extra interactions which accompany the interaction of interest. So that's discovery. The LHC and CMS work magnificently. This 3-year row is now completed. We've discovered a new one. It's generally compatible with the standard model boson, but the other really is that boson is the way. Measuring its decays more precisely, measure its spin and its symmetries, much more data in July. So one way or the other, we will soon have Higgs boson in the model. But we know that in theory, which is more fundamental beyond this model. The search for this theory has done, and Caltech is way. And beyond, it will take a generation of physicists, now maybe we're talking 2 generations, to figure out what the heck is dark energy. So this was very fast. And so further information I can book by Owen Carroll, The Part and the End of the Universe, another book by Lee Randall, and some other sources you can find. Some mention this is Science Magazine, Breakthrough of the Year, a beautiful article, December 21st of something to explain to a wider audience, to a wider discussion all. Finally, for those on physics and actually difficult in themselves. And so much, I enjoyed it.